Hey guys, BuildZoid here, and today we're going to be taking a look at this monstrosity right here. This is a GTX 1080 FTW that I picked up on eBay a long time ago, which funnily enough at the time I figured paying 100 quid for a dead GTX 1080 was kind of a lot. But thanks to the current GPU shortage, even now dead GTX 1080s still go for around 100 quid, so actually, that was a pretty good investment. Not really, but anyway. Yeah, it's a dead GTX 1080 FTW, and of course the reason why it is a dead GTX 1080 FTW is pretty simple. These have a VRM, well, basically these cards have faulty VRM components. So I'm not sure how many cards are affected, but eventually a lot of them end up with the VRM exploding and putting a crater in the PCB, sort of like you can see right here. Now, if you have a crater like this in the PCB, one thing you can do is like drill out the entire area and try to like remove all the short circuits, and then and then you get the card up and running again, but then it's like technically that failure occurred because the VRM is fundamentally like flawed due to the faulty components that are in it. So I'd say if the card blew up once, it's probably going to blow up again. And you're just going to be steadily removing more and more of the VRM. Either way, I don't really have the equipment to properly remove short circuits like that. So that wasn't really, like, for me, that's not even an option or even a consideration. What my solution to the problem is very simple. Just bypass the entire Vcore VRM, because if we go around the exploded part of the card, well, we don't have to worry about fixing the exploded part of the card. And so that's exactly what I did here, which is this extra board over here. So that's the Galax Hall of Fame e-power. It's a 16-phase Vcore VRM. Well, 16-phase VRM. Well, here it's being used for Vcore because that's the part that blew up on the 1080. But it is just a 16-phase VRM. If you wanted to, you could use it to power the memory. It would be totally unnecessary, but you technically could do that. Anyway, yeah, 16-phase VRM based on the Vcore VRM of the GTX 980 Ti Hall of Fame LN2 like special edition. This is an absolute beast of a VRM, like 16 phases of 60 amp power stages. Obviously not true 16 phase, it's doubled, but that doesn't really matter. Like, yeah, an absolute beast of a VRM designed for powering 980 Ti. So massive overkill for 1080s. But the thing is, I don't really, well, yeah, I didn't really have a convenient VRM to stick on the card to try fix it. I do actually now have an alternative VRM that is going to go on here once I'm finished with running this card on LN2, because there's, like, this is a really nice VRM, so, but it's also totally overkill for the card. So once I'm done running this in its current condition, the plan for the future is actually to rebuild it with a Vcore VRM off of a GTX 780. That's a bit more, appropriate for a GTX 1080 core. And actually the way I want to install that should accommodate the stock heatsink. So I'm kind of excited for that. But for now, we have it in this sort of like, well, basically built for LN2 overclocking setup. Because that's the plan, is like I do want to take this card on LN2 pretty soon. And that's been getting delayed mostly because I wanted to show you the card without everything covered in Plastidip. Because it's kind of hard to see things when they're covered in Plastidip. So, yeah, anyway, it's running. It's actually been kind of running all day because I've been procrastinating most of the day run it. I've been procrastinating on recording this video most of the day. There, I am very good at English. It's actually more of an issue of organizing my thoughts. But anyway, yeah, also there's a memory voltage mod to get like memory voltage control. Actually, we'll go over the mods after we do a little proof that the card works. Like, of course it works. So yeah, here we are in the operating system. The card is overclocked. This isn't maxed out. This is just some overclock I threw on there just for the sake of being able to demonstrate that it does overclock. And yeah, it'll run Firestrike. The 5950X is currently at stock settings, so the score is not going to be super amazing. Though even a stock 5950X absolutely destroys Fire Strike physics, so yeah, like it's still going to be a pretty high score, but I've already posted a higher score with this card to Hardware Bot. We're just not going to take a look at that because I want to show the card actually running. And you've probably noticed that the two 8-pin power connectors aren't plugged in, and that's just because the power board, the Hall of Fame power board takes 3 8-pin power connectors, or actually I've modified even that to take 3 6-pin power connectors, because plug-in, like the split 6 plus 2-pin power connector is really obnoxious, so I modified the 8 pins on the power board to just work with a 6-pin instead, because yeah, I don't feel like plugging in all 8 pins. That's literally it. I'm incredibly lazy, and that's my solution to the problem. But the card itself, the two 8-pin power connectors have actually been wired to the PCIe slot, because the only thing on the card that still runs off of the main 12-volt like power is the memory VRM, and the card runs GDDR5X. I see no reason that it would pull enough power to overload the PCIe slot, so I've just wired the memory to the PCIe slot. So yeah, by basically wiring all of the 12-volt power on the board to the PCIe slot. But since like the only other thing that's really on a GTX 1080 is the Vcore VRM, and I've replaced the Vcore VRM, that's not really a concern. So yeah, so that's what's going on with the two 8-pins not being plugged in, is just like, well, they don't need to be plugged in because the card runs off of the like the 3 8-pin, well, 3 6-pins for the E-power, and then the rest of the power is just handled from the PCIe slot. So that makes it a lot more convenient than some of the other cards that I've E-powered, where you still need to plug in like a 6-pin power connector, and then with how little space there is between the power board and the connectors, like getting getting them plugged in, not that bad. Getting them unplugged, not fun. So yeah, that's the main reason why the card is wired up this way, where it pulls a ton, like all of the extra power from the PCIe slot, because I don't really want to deal with having to unplug a power connector from that. Also, just having 4 power connectors on a 1080 is stupid. Like, yeah, honestly, like, you can run a GTX 1080 Ti off of just 2 8-pins, even on LN2. There's really no reason to need this many power connectors. It's just the power board is designed for, like, well, anything, right? Like, it's a 16-phase Vcore, so if you wanted to power something really, really power-hungry with it, you could, and it has the connectors necessary to do that. A GTX 1080 is just not that. Anyway, so Fire Strike just finished. You know, gets a decent score. Card was running, what is it, like 2100? Yeah, 2100 core for the graphics tests, and then 1461 for the memory, which it just runs constantly. Max temperature was 48 degrees Celsius. Actually, we have a hotspot readout, and that was maxed out at 60 degrees Celsius, so that looks good. Oh, and the power consumption on the card is a bit whack. It actually goes down under load because of how the current sensing circuitry's been because the thing is, when you replace the Vcore VRM like this, like I've disconnected a lot of the stock 12-volt power delivery, and so the NVIDIA drivers get very upset if they get fed some really weird 12-volt data. So what you need to do is you need to fake your 12-volt power readings so that the NVIDIA drivers don't freak out. And the way that I've done it on this card is a little bit lazy, in that basically I've still not sure why it drops as much as it does, but basically there's a voltage divider off of the 12 volts on the card. That's I think 33 ohm resistor into a 120k ohm resistor. So that goes 12 volts, 33 ohms, and then 120k to ground. And this gives you a very small voltage drop across that 33 ohm resistor that you can feed into the low voltage side of the shunt monitoring chip. And then the high voltage side, you just sort of leave that alone. And you get this situation where the card basically, like, no matter what happens, I don't think it'll ever read more than, like, 22%. In fact, minimum power reading is like 9.5%, and the power reading actually goes down based on how much load the card is under. Which, I wonder if we can do that with just the GPU Z render test. Yeah, so you can see, like, the power reading drops off a cliff when you run anything. So that's fun. Like, the main thing is, as long as the GPU is hitting, like, because the problem is, if you screw up the power reading too much, what'll happen is you'll actually not get full 3D clocks. So that's sort of the main reason that, like this right here is a little bit on the low side for my tastes. Normally, I aim to have these kinds of, like, power limit removals to hover around the 50% mark. Because you're definitely, like, you definitely have room both up and down if you're at 50%. But also I could just plug in one of the 8 pins and it would actually change that 12-volt power rating. Because, yeah, it's not like the main thing is the power management chip is convinced that there's nothing wrong, even though these power readings don't make any sense. That's not my problem. The driver's okay with this. So, and if the driver's okay with it, I'm okay with it. So, anyway, yeah, so card overclocks, scores pretty well. I think I got a reasonably high score out of the card for the Firestrike rankings on HardwareBot. But of course the plan is to take it on LN2, but before I do that, I want to show you all of the modifications that I've done to the card, and I just realized that now I need to, like, shut this thing down. I guess I could have used the power button instead of the shutdown button, instead of doing it through Windows, but yeah, anyway, let's take a closer look at the monstrosity that I've built here. So, switch off the power supply, unplug the too many 6 pins, and I still left some flux on the board. Did I? Oh, nope, that wasn't flux. Good. Anyway, let's unplug that, and actually at this point we're just going to hide this so that we have more space, and come on, there we go. So yeah, here's the front of the card. This is actually, like, by far my cleanest e-power build ever. And we'll get to that once I get the cooler off, because right now you can't really see anything. Anyway, this heatsink, this is a Thermalright Shaman heatsink, if I remember correctly, and this thing's really, really awesome. Like, I'm a huge fan of this heatsink because it's got a lot of, like, well, it has 6 heat pipes, I think. Wait, no, 8 heat pipes, and it does a great job of just cooling anything. I think it was originally designed as, like, a replacement heatsink for GTX 480s. And so, yeah, it's really, really capable of just cooling most GPUs. I guess with a 3090, it probably wouldn't be ideal, but I'd argue that's more because of the memory chips than it is about the core in that scenario. Because, yeah, really good heatsink, but what I really like about it is, compared to, say, a Morpheus or something, this actually clears an e-power properly, right? You can see it just barely makes it over the connections. So that's my favorite part about this heatsink, is that I can actually use it as, like, a really good test heatsink with e-powers, as long as I just keep the angle of the e-power relatively low. Obviously, if you, like, the funny thing is, if you want to make your life easier building an e-power, you just stick the e-power 90 degrees up, relative to the board, but then it's like the heatsink situation gets really, really awkward instead of just kind of awkward like it is here. And it's only kind of awkward because I even have this heatsink, because this is not exactly a super easy heatsink to find, because it is quite old, and not really that common, right? Like, custom heatsinks aren't that popular in the first place, and this one is really pretty old. I've also replaced the mounting hardware on it because I didn't like the stock mounting hardware. I don't like the stock mounting hardware on most heatsinks, I'd say. And I've realized I don't really want to rest that. It'll be fine. Just put that on the board. Anyway, so here's the back of the card. Well, I do need to get the heatsink off, but yeah, obviously I've gone ahead and done some cap mods. The Vcore ones are actually somewhat useful. Like, they make a noticeable improvement in peak-to-peak voltages on the oscilloscope, though I'm still, you know, at the same time, I do consider the peak-to-peak measurements kind of the measurements you look at when you want to feel good about yourself, rather than actually look at the measurements that make a difference. The thing is, I wasn't really tracking the minimum voltages that well. I wasn't paying that much attention to the minimum voltages. And if I remember correctly, those either didn't improve or improved very, very, very slightly. Which is probably why I didn't bother tracking them. Yeah, but honestly, like, the crazy thing is, this was actually a 200 millivolts peak to peak, without any of the cap mods. Like the initial, and without the power bridge or anything. Like right out of the gate, this actually had quite good voltage regulation, like 200 millivolts peak to peak. After you replace the Vcore VRM like I did, I was expecting like 300 or something horrible, you know. But 200 millivolts peak to peak, that's actually pretty much in line with like stock cards. Like a lot of cards from the factory will be somewhere around the 200 millivolts peak to peak mark. And so, yeah, I was really pleased with that. Obviously, I've got the card on, what's it called? Thermal Grizzly Cryonaut Extreme, because Cryonaut Extreme is, well, I have tons of Cryonaut Extreme, and it's great for LN2, and I really don't want to have, like, contamination between, like, a test paste and the Cryonaut for when I take the card on LN2. Though the E-Power does make it really awkward to mount LN2 pots, just because it makes the card really VRM side heavy, so, like, getting the card level when you're installing it is a pain. But yeah, this right here is like by far the cleanest E-Power build I've ever done. Partially because I got a new soldering iron that I basically tested by doing this. So I got a JBC soldering station, and yeah, it's amazing. Especially the 6.6 millimeter chisel tip is just so good, especially for stuff like this. And then also this wire stuff is awesome. Because this looks a hell of a lot like desoldering braid, but it's not desoldering braid. So desoldering braid is basically copper braid with some flux in it. This stuff is tinned copper braid, and it's like rated for 30 amps current carrying capacity. And yeah, and there's just a website here in the UK where I bought this stuff from, like a whole spool of it. It's not that expensive, and it's so easy to work with, because compared to, like, you know, you see like it has a ton of cross section, and compared to using, say, copper plate, this is a lot more flexible. Like, it has a lot more give. It wets really well. Like, yeah, it's super easy to solder this stuff. Also, copper plate is just such a massive pain to work with, because like getting it bent properly and that kind of thing. So yeah, I'm really pleased with this connection right here. There's very little voltage drop on the card. Like going from, basically, if I measure the voltage between these two pads on the E-Power, and then I measure the voltage across the capacitors back here, it's the same. Like, it's exactly the same. You get 1.09 volts on the back, you get 1.09 volts on the E-Power under load. So yeah, this works really, really well. For making high current connections like this. What's actually kind of funny to me is the PCB of the card itself has more voltage drop than than this connection over here, which is why I have the three like high current wires on the back here, because basically when I was testing the card, what I noticed was that you know, like I'd get 1.09 volts in this area of the PCB, but if you measured behind actually not even behind the core, if you measured, like, you see these two like points over here, this is where I'd have the oscilloscope hooked up. So this would actually be measuring a lot lower voltage than right here, and that's also where I was taking my like peak to peak measurements and everything. But anyway, so I'd be measuring a lot lower voltage over here. Like here, we'd be getting like 1.04 volts, 1.05 volts, right? It would float around a bit depending on how much current the workload was pulling. But over here, you'd have 1.09. So it's like, well, you know, obviously the problem isn't this side, like, isn't this connection over here, because I have 1.09 on the board. I have 1.09 on the other side of where those connections are made. So we're not losing any significant amount of power in that connection between the E-Power and the PCB. All of that voltage is getting lost in the PCB itself. And so I added these wires on the back, and those knocked it down from those knocked down the voltage drop by 30 millivolts. So it went from 1.04 volts behind the core relative to 1.09 over here to 1.07 relative to 1.09 over here. So huge improvement. And this has to be the first time I've actually done a power bridge where it was worth doing. So I'm really, really pleased with this stuff, but it also makes sense. This, like, is way, way higher current capacity than, like, 18 gauge cable. So that makes sense because in the past I usually try to do power bridges with 18 gauge cable, and yeah, compared to this stuff, 18 gauge just kind of sucks. Yeah, don't bother with 18 gauge. Like if you want to do power bridges, use this. If you want to do e-powers, use this. This stuff is freaking awesome for just high current connections, and yeah, I'm surprised it took me this long to discover it because it works so freaking well. Yeah, so that's sort of what's going on with that. Then you might be wondering about these large magnet wires along the edges of the card. These are not for any kind of power delivery. These are just for structural bracing of the PCB, because one of the problems with e-powers is that, well, they're heavy, right? Like this, like the card is very significantly heavy to that to the side where the e-power is. And the thing is, if you don't really like, you can see I have like supports here to make sure that the e-power basically isn't like flexing the PCB too much. Also, actually, there's a kind of sneaky connection. Yeah, you can see it back there. So that's another ground connection. So all of this on the front, this is all ground, and that right there is also more ground. It's not anywhere as this isn't as effective, obviously, that, because ultimately, like, yeah, we have this really thick connection running across the length of the PCB, because there's like a bunch of input filtering capacitor pads there. And so one side of those is obviously ground, so I use that to get another ground connection over there. Not really, like that doesn't really make that much of a difference, you know, compared to what I have on the front here, but hey, it certainly doesn't hurt. Oh yeah, then we have the memory voltage mod, so potentiometer for raising the memory voltage up and down. Actually, just raising the memory voltage, in this case, it's GDDR5X. GDDR5 scales positive, so if you just keep adding more voltage up to around 1 point, I think it's 1.5 or 1.55 volts, is about as high as it'll scale. And I also have a switch to turn the voltage mod on and off, just in case that, you know, I don't want to use it for any reason. Yeah, here you can see how the 8-pin power connector is jumped. You can also see that I have a bit of wire to... because the thing is, 8-pin power connectors have 2 sense pins in them, and those sense pins, all they do is they just detect if the power connector is, if those pins are grounded, so they basically check that there's a connection to ground. So that's what's going on with that second piece of wire, like that silver piece of wire in the 8-pin there, is just it connects all of the sense pins to ground, so that the card doesn't complain, hey, you don't have your power connectors plugged in, because... if you don't do that, you'll actually just get an error message telling you, hey, you need to plug in your 8 pins. And it's like, but I don't want to plug in my 8 pins. Like, it's the whole freaking point of having this yellow wire over here. And that yellow wire, you know, connects over here. Also, this red wire supplies 12 volts to the, I think it's the 5 volt regulator. It might be the 1.8 volt, right? I don't know. I'm pretty sure that's the 5 volt regulator. Either way, there's like a minor voltage rail here that, that is providing power to, because... well, the original power delivery trace exploded when I hot wired it, so... and the hot wire is the red one over there. Also, there is flux on that part of the board, and I just touched it. Ew. Yeah, we're just going to wipe that off on a different part of the board. Anyway, you can see that yellow wire comes in over here, and then it grabs 12 volts from the PCIe slot over here. And also here you can see that 33... I think it's 33. Yeah, I'm pretty sure that's 33. So, 33 ohms... 120 kilo ohms ground on this side, and then you can't really see it at all, but there's like a little split between the the filtering capacitors right at the INA3221 shunt monitoring chip, because it has a bunch of filtering capacitors so that like it doesn't pick up on super fast transients. So it has like an averaging, like basically those capacitors are there to average the power readings a bit. And so, yeah, but they also act as really convenient hookup points. So that's where the power monitor, like that's where I fake the voltage reading, is just feed this fixed voltage division, fix this fixed voltage drop into the shunt monitoring chip, so that it thinks that there's current flowing through shunts that are not physically present on the card any longer. Like there's literally 0 shunts on this card at this point. There are no more shunts, at least not that I'm aware of. So, yeah, other than that, the card also has a dual BIOS switch, which is sort of like buried in between my memory vault mods over there. And there's also a memory voltage limiting resistor that you can see sort of hanging out in there. I think that's set so that it goes up to 1.6 volts. I've not checked, but that's there just in case, you know, I screw up and set the voltage too high. Anyway, what else is there? That sort of covers most of it. Oh yeah, the cap mods. So the cap mods behind the core, I mean, I already mentioned those knocked it down from 200 actually, did I mention that? Anyway, if I didn't mention, the extra capacitors behind the core are, whoa, actually these power bridges make it really hard to see what I did there. Because there's a bunch of extra multi-layer ceramics that I added. All right, you can see, yeah, you can kind of see that I've stacked some 22 microfarad 0603 multi-layer ceramics right down the middle. Like there's a row right down the middle of the core. So I added those. Then of course we have the bigger polymer capacitors. I think those are 1200 microfarad. Let me check. Yep, those are 1200 microfarad. So we have some 1200 microfarad Nichicon FP RS8 series capacitors. So those are like low ESL through-hole polymers. They're still worse than the SMD polymers or SMT. Well, the molded polymers, but I added 2 of those as well. So there's some 470 microfarad SP caps stacked on the stock. Stacked on top of the capacitors that the card comes with from the factory. And yeah, and this extra set of capacitors knocked the peak-to-peak voltage readings down from 200 millivolts to 160 millivolts, which, you know, it's like, it's not a huge, like, it's not the lowest peak-to-peak that I've ever measured, but it's also better than 200, so I'll take it. So yeah, so I'm pretty happy with that. Then I tried, obviously we can see that I've just gone to town on the memory section, right? We just have extra multi-layer ceramics absolutely freaking everywhere for the memory. Those helped a little bit. I didn't really take too much note of it. It's not as, like, the effect of these is not as significant as what I saw with a GDDR5 1070. Which I'm kind of sad about, because I had a 1070 at one point in time where you added capacitors to the memory, and it was just huge improvement in memory overclocking headroom. And then there's this thing where you do the same thing, and honestly, it just scales far more from the memory voltage than it does from the capacitors, but they don't hurt. The big bulk ones were totally unnecessary, though. Like these 4 caps right here, totally unnecessary. Those are 560 microfarad RS8 series Nichicon FP caps. And yeah, they made absolutely no freaking difference. Like before and after didn't change anything. Totally pointless. I'm not gonna take them off because they also don't hurt anything. But yeah, what a waste! Like I'm kind of annoyed by how much space they take up around the core, and they might make insulating a bit more awkward. But yeah, it's not the end of the world, so I'm not too bothered about getting rid of them. And I think that covers it. Yeah, like, honestly, this is a really nice, like, this is by far my best e-power build, right? Neatest, most functional. I need to, like, yeah. Well, actually, no, definitely, neatest, works the best. Admittedly, I've not checked the GTX 480 e-power on the oscilloscope, but I tried checking the Titan X on the oscilloscope, and that thing runs horrible. And I'm not sure why, but it runs really, really awful. That thing gets like 350 millivolts peak to peak. And the crazy thing is, I've tried all kinds of stuff to try fix it, and it just doesn't budge. It's horrible. So yeah, I'm really not sure what to do about that card. I've kind of suspect that might just be a Titan X Maxwell thing, but I've never had like a healthy Titan X to compare against, so I'm not sure. Whereas this just works well. Like I'm just pleased with how well it runs. Also, this is a really easy card to power mod, like, well, to e-power like this, because you have a lot of ground right over here, and there's a lot of stitching, which I'm a big fan of, because like there's a lot of via stitching for the ground right in this area, because sometimes you try to attach to like bulk capacitors for your Vcore or your ground connection, and it just kind of doesn't work because the capacitors don't really have that much that strong of a connection to the ground plane as, say, the actual power, like as, say, the actual power MOSFETs. But the power MOSFETs in a typical e-power build are under the e-power. So, you know, trying to solder any connections down there is not really, well, I mean, if you stick the e-power, like that's the thing. If you stick the e-power 90 degrees relative to the board, yeah, sure, you can make use of those connections and it works really well. If you want your e-power lying flat like I did, you're not really going to get in there. So, yeah, also, if you're wondering about what this is, that's just more ground, right? Like, you can see that or I guess maybe, yeah, no, you can see it on camera right now. Like, that's just the ground side of the capacitors, because these capacitors are for the memory VRM. The caps that are hidden under this are actually for the Vcore. You can see two of them over here. I didn't do these two because there's a bunch of little SMD components over there, and yeah, it's just no way for me to get the big soldering iron tip into that area without screwing up stuff, so I didn't do that. But like the card has so little, like this connection drops basically no voltage. All of like the vast majority of the voltage drop in this e-power build is actually the card itself, not this. So I like evidently this is more than enough. So yeah, I'm really happy with how this turned out. I think I also had to remove maybe some power sequencing transistors at some point in time, but the thing is, like, I actually prepped this card. Well, so the card has a bit of a story to how it, like, when I first got this card, I actually test fired it with the Hall of Fame power board. And so it was already sort of prepped for e-power for ages and ages and just sitting in a drawer until recently I was like, well, I got the new soldering station and I was like, I want to test this with something like really difficult, like an e-power build. Because the thing is, when you're soldering, because this is all just soldering Vcore main power plane to the output of that power board, and that power board has a lot of thermal mass to it. And then also you don't really want to take off the heatsink from the e-power because you're not going to get it back on once the e-power is installed. So, you know, you're kind of so the heatsink on the power board is fighting you as well. Yeah, like these wires work great. The new soldering station is amazing for this kind of thing. It's awesome. Yeah, what else is there to say? Oh yeah, and this just works really well. So yeah, now I just need to prep the card, like insulate the card and take it on LN2, which has been getting continuously delayed as I've been delaying the recording of this video, just sort of showing the card before everything gets covered up. So yeah, and my hopes are that I get the card to do at least, I mean, on air cooling it does 2100, so I hope to get at least 2400. The thing with Pascal is that most of the struggle is getting the thermal paste to stick all the way down to full pot. So actually, let's talk a bit about the LN2 prep that I want to do. So, because, yeah, I guess video continues. We're not at the end yet. So for Pascal, what I really, so I have this on one of my 1080 Ti's. Basically, I'm going to glue a K-type thermocouple. Or actually, I'm probably just going to plasti dip it into place. Man, the more I think about it, this whole capacitor situation over here is just like, if I ever want to take that plasti dip off, it's not coming off. Like, it is not, well, no, you can always use plasti dip solvent. Yeah, like worst case scenario, if you plasti dip a card which looks like this and you need to peel it off in this area, you just have to use solvent at that point. You just have to melt it off instead of, like, well, wash it off instead of trying to peel it off, because you're just going to rip everything to shreds otherwise. But yeah, I'll just dip the K-type thermocouple into place right behind the core. And the reason I do that is because you can have one K-type thermocouple on the LN2 pot to potentially control the temperature if the card turns out to have a cold bug, which some Pascal cards do have, that they don't work at a, like there's a temperature range where they don't work, and they work above that or they work below that. There's also some cards that just don't work at all below a certain temperature point, below a certain temperature, which is really unfortunate. But a lot of cards will actually go all the way down to full pot. The main problem is that they also break, like they crack the thermal paste super easy. And so having a K-type thermocouple on the back of the core is super helpful because you can really closely monitor the temperature delta between the LN2 pot and the back of the core. So if you're running, so basically as you cool down, you would run like Firestrike or something, and on the back of the core you might see like, I don't know, let's say you start at minus 100, because down to minus 100 things tend to go pretty easy. So you start your stress test, or, well, yeah, stress test at like minus 100, and you'll see like a temperature delta of maybe, I don't know, 40 degrees Celsius. Okay, like a pretty significant temperature delta. It's because you're on the back of the card, the cooling's all the way on the front, right? You have to consider that the heat in the chip is not generated at the top of the chip, it's generated at the bottom of the chip. So the heat actually, like, you know, the LN2 pot might be at minus 80, but the back of the chip could easily be far higher temperature than that. And then, of course, the card itself is exposed to the ambient air. So the back of the PCB is naturally going to be warmer than even the transistors at idle. So once the transistors load up, you're going to get a pretty big temperature delta. But the thing is, you can track that the temperature delta is consistent, right? Because that's kind of the thing. It's not about going like, oh, this temperature delta is too high, because, like, well, after you've measured your temperature deltas with good thermal paste condition, you can actually make judgments like that. But at the start of the session, you won't know. So let's say you start the test at like minus 100, and the back of the core is going to read like maybe minus 60. And then you go down to minus 120, and at that point, the back of the core should be reading minus 80. You go down minus 140, the back of the core should read minus 100, you go down to minus 160, you get the idea, and you work your way all the way down to minus 196 degrees Celsius, or minus 190 probably under load. You know, the LN2 pod isn't going to be exactly at the same temperature as the liquid nitrogen, but, you know, you get down to somewhere around minus 190, and the back of the core should ideally be somewhere around minus 150, maybe minus 140, because obviously, you know, ambient air temperature means that the back is going to want to tend positive, not negative. So the delta is going to sort of spread as you cool down on its own a little bit. But then if you're but what can happen when you're doing this cooldown process, instead of getting down to minus 190 and measuring minus 150 or minus 140 on the back of the core, you might end up at minus 190, and the back of the core is at minus 100 or minus 80 or minus 60. And it's like, so at that moment where you start seeing that, like, your LN2 pot temperature keeps going down, but the back of the card isn't cooling down, that's kind of when you go like, oh, I think the thermal paste failed. And normally, yeah, your thermal paste failed if that starts happening. So that's why I really like to put that's why I'm going to be, you know, putting a thermocouple on the back of the card, because with Pascal, like, it's about getting the card as cold as possible, and then you can start raising the voltage, because at ambient, these cards basically don't scale with voltage, and at minus, say, 50, you get some voltage scaling, but not insane. Like, it doesn't scale to some crazy high voltages, so you really need to get the card as cold as possible, and then hopefully it'll scale well. And 1080s aren't very, like, there's not a lot of 1080 scores on LN2. Like, these cards didn't get as much attention as the 1080 Ti's, which makes sense, because the 1080 Ti is faster, but yeah, and so 1080s are sort of not known to clock as high as 1080 Ti's, which is super weird. But I'm kind of hoping, you know, like 2300 should be easy. Like, I honestly think this should hit 2300 at maybe minus 100. And so I'm really hoping that I could do at least like 2400 to 2500 at minus, you know, if I get it to full pot, I'd like to do minus 240. I mean, 2400 or 2500 core is kind of what I'd be hoping to squeeze out of this thing. But yeah, like, we'll see. And in theory, I should be able to sort of mop up all of the top scores for the GTX 1080, because between this and the 5950X, that should be quite easy. There's really not that much competition for, you know, putting 1080s on LN2, and yeah, it's like, it shouldn't take, like, as long as I don't have too many issues, which, you know, I plan to take it relatively slowly. Because the thing is, when I was benching the 1080 Ti on LN2, if you actually made it to minimum temperature without any issues, it could stay there for like an hour or 2 hours, or like they're relatively stable cards if you have your insulation done well. Another thing is actually you want the memory to freeze through on these, because the GDDR5X from Micron scales with low temperatures. So yeah, it should be really fun. And I don't have to worry about like any power delivery, because freaking 16 phase. Also cap mods for days. So yeah. Oh, actually, no. The last thing I want to mess with is actually that hook, like those two read points over there. I want to run the card with the oscilloscope hooked up on LN2, because I've never done that yet. Like I've run the like I've watched stuff run on the oscilloscope. I know I did that technically. I did that with the 3060 Ti, but I wasn't taking that too seriously. Like I wasn't slamming that 3060 Ti. Whereas this thing, you know, it's literally a card with a hole in the PC, with a crater in the PCB. When I got it, it was totally non-functional. What's the worst that could happen, right? So, yeah. Yeah, the main thing, though, is going to be making sure that the thermal paste is stable. So I'll probably take it pretty slow, because I think even at minus 80, if the scaling is halfway decent, it should put out some pretty good scores at even like minus 80 degrees Celsius. And then below that, you know, we'll see if I can push it really, really low. I hope I can. Like, I really hope I can. Because not having to worry about, like, full pot GPU benching is just so much nicer than having to worry about the temperature. So, yeah, anyway, that's the GTX 1080 FTW Zombie. And then once I'm done with running it on LN2, like, yeah, I'll just slap a GTX 780 VRM on it. So yeah, that's it for the video. And man, this turned out way longer than I figured it would, but anyway, yeah, so GTX 1080 FTW had the VR, like, did the typical GTX 1080 FTW thing of having the VRM explode. Well, VRM explode no more, because it's no longer on the stock VRM. So yeah, that's it for the video. Thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store, where you can pick up shirts, stickers, posters, you know, the usual YouTuber merch. Both Patreon and Teespring help out immensely with running the channel, so it would be much appreciated if you check them out. And yeah, that's it for the video, so thank you for watching, and goodbye.